Hello. Hello. Am I audible?
Yes, sir.
Okay. So in the last lecture, what we have done. So actually, we were discussing about that Raman spectra of the CO2 molecule. Okay. So in the last lecture, what we have discussed that the carbon dioxide CO2 molecule, there are three fundamental vibration. Okay. There are three fundamental vibrational modes. So out of three vibrational modes, first one is the stretching mode, which is the Raman active. Other two are the bending mode and asymmetric stretching. Okay, so other two modes are found to be Raman inactive. These are not active. These are inactive. Okay, whereas in the case of the H2O molecule, all the three modes, that is the symmetric stretching mode and the bending mode, and third one is the asymmetric stretching mode. All the three modes are found to be Raman active. Okay, so why is the case a different case in in the case of the CO2? So let us try to understand it. Okay, so here we will have the three modes, and these three modes, out of these three, only one is found to be Raman active in the case of CO2. Okay, so let us try to understand this different Raman spectrum in the case of the CO2 as compared to H2O. So if you take the, so we are discussing HCO2 molecule. Okay, so three fundamental modes of vibrations are there: nu 1, nu 2, and nu 3. Nu 1 is actually the symmetric stretching. Symmetric stretching mode. Okay, second nu 2 was the bending mode of vibration. Third one is the asymmetric stretching. Okay, so this first mode was Raman active. Second mode was Raman inactive, not active. Raman inactive. Third mode was again Raman inactive. Okay, so let us try to understand why it is so. So this can be understood by, let us try to discuss the change in the polarizability ellipsoid with respect to the displacement of the coordinates. Okay, let us take the change in polarizability with respect to displacement coordinate. Okay, let us call this displacement as zeta and polarizability is the alpha. Okay, so we will draw the curves here. So we have this. This is for the first mode, that is symmetric stretching mode. Second one is the bending mode. New 2. Third one is the, for example, this is the new 3, that is the asymmetric stretching mode. Okay, so the in this symmetric stretching, what is happening there? So for example, this is the y-axis and this is 0. Okay, and for example, this point here, this will represent the alpha naught. Alpha naught is the polarizability at the equilibrium. Okay, you can say the equilibrium polarizability. That is the polarizability of that particular molecule without any kind of stretching or bending. Okay, and so this is the positive. This is the positive part, is that positive zeta. It means that there is a change in the positive direction of the, you can say the stretching in the positive axis, and this is the negative zeta, means this change in the bond length of the particular molecule in the negative x-axis, you can see. Okay, so zeta is basically a displacement coordinate. What is this displacement coordinate? That what is the basically, you are just changing the bonds. Only the first bending, symmetric stretching, you are just stretching or contracting the bond length. Okay, so this zeta is basically giving the that coordinate. You just stretch or compress the bond. Okay, what happened to the polarizability? Okay, so y-axis we have polarizability. Okay, so this is zeta upon zeta respect to alpha. So what happened to at the this new at this any equilibrium position, the polarizability is alpha naught. That is the alpha naught is the equilibrium polarizability of that particular molecular ellipsoid. Okay, so when you change, when you elongate the bond, so what happened? Polarizability will be changing like this. Similarly, when you just decrease the bond, it will be changing like this. Okay, so this is the case when there is a symmetric stretching of bond. So this curve basically represent the polarizability versus the displacement coordinate. Displacement coordinate means changing, small change in the bond length of that particular molecule. In second case, we have bending mode. So in bending mode, how can we just define this curve? So in bending mode, let us assume that this is the y-axis. We have alpha here, and positive zeta is here, and negative zeta is here. Positive zeta here. So here the changing in this change coordinate is the, you can say the change in the angle. Okay, this is the change in the angle of it, because you are bending the that particular molecule. So change in the angle, you can say. So here it is the equilibrium polarizability is the alpha naught. This is alpha naught. Okay, so when you change the angle, okay, so this you have seen that, you can see here in the second case. Okay, that was the bending mode. So this was initial case where the polarizability, here it is the alpha naught is the equilibrium polarizability. So when you change the bond angle like this towards the lower side, it will the polarizability ellipsoid will looks like this. Okay, when you change in the negative axis, okay, so the polarizability ellipsoid, it will looks like this. So there is an equal change in the bond angle in the opposite direction, equal in opposite direction. So that's why the if you see the polarizability curve here, So it will be looking like this. Okay, so this is the alpha naught. In the third case, where we have the asymmetric stretching of the bonds, okay, this is asymmetric stretching of the bonds. So here the polarizability versus displacement coordinates, this curve will be like this. So we have this y-axis alpha. Okay, here it is the equilibrium polarizability alpha naught. So in this case, it is assumed that the polarizability will be there will be small decrease in the polarizability. Okay, this is the positive zeta, negative zeta. So there is small increase. It is assumed that there is small increase in the case of bending mode, and in the asymmetric stretching, it was assumed that there is very small decrease in the polarizability. So polarizability will be looking like this. Curve will be looking like this. So these are the three different curves for the polarizability versus displacement coordinate. Okay. Now, if you see the respective slopes of these curves, okay, if you see the respective slopes, so if you see here at the this point, slope is going to be like this. If you draw slope at that point here, it will be like this. Okay. And if you draw the slope here in the second picture, you will see that at that point, it is like very small slope. It is here, very small slope is there. Similarly here, slope is very small or nearly zero actually. Okay, so here if you
Excuse me, sir.
yes please.
So can you repeat this curve again? Means how we can plot this curve?
These curves,
Yes, sir.
these are actually the curves between the polarizability versus the displacement coordinates. Okay, in the case of the first case, we have symmetric stretching. So what happened in symmetric stretching, that there is the change in the polarizability left side because there is a change in the size. If you see in the last lecture, we have seen that there is a significant change. See this picture. There is a significant change in the polarizability curve, polarizability left side. So there is significant change. It is when you increase when you just compress the bond, the polarizability left side size will be increasing, and when you just increase the bond length, CO bond length, you will see that the polarizability left side size it will decrease. So there is a significant change in the polarizability left side size of the polarizability left side. So because there is a significant change with the changing the polarization this displacement coordinate, that is the bond length between C and O. So the curve is like this is a very sharp change with the in the polarizability with respect to the displacement coordinate. That's why there is a sharp increase in the polarizability in the positive axis, a sharp decrease in the polarizability in the negative axis. So that there is a large slope at this zeta equal to 0. Okay, at zeta is equal to 0, there is a very large slope you can see here. In the second case, what we have seen that when you just draw these polarizability ellipsoid in the bending mode, what happened? The the size of the polarizability ellipsoid will not change much. Okay, it will remains nearly same, although slight change in the shape is there. Okay, shape is changing slightly, but the size will remain same. slightly, but not very significantly. Okay, but the size of the polarizability ellipsoid will remains nearly the same. So if this is the case, so what happened when you change? So displacement coordinates, so polarizability with respect to displacement, when you draw a curve, it will be changing in a you can say that there will be increase, small increase in the it was assumed that there is small increase in the polarizability actually, but the increase is actually, so you can see this is symmetric increase and decrease. If you see the bending, so there is a change that you can see these are nearly spherical ellipsoid, this polarizability ellipsoid. Okay, actually there is this increase and decrease in the bending. So bending is equal and opposite. Okay, so that you can see here, so there is just a small increase. There is small increase like this. So curve will be like this. And in the case of symmetric stretching, again, the size is slightly changed. It is not significantly changed. Slight change in the size of the that particular uh, polarizability ellipsoid. In the case of asymmetric stretching has been observed, so that it was assumed that the actually this polarizability is inversely proportional to the size of that particular ellipsoid. Okay, so that it is slight decrease in the polarizability curve. Although because actually this change is very small. Okay, it is looking in the curve that there is a large decrease, but it is not actual. Actually, this decrease is very small. So that if you see if you find out the slope at the zeta equal to 0, so we see that in the two cases, in the two mode, nu1, nu2, and nu3, bending mode and asymmetric stretching mode, the slope is very small. Okay, and in the case of the first case, there is significant change in the size of the polarizability ellipsoid in the both the direction, so that the slope is going to be large. Okay,
Thank you, sir.
so if I just yeah, so if I just add zeta equal to 0, if I find out d zeta upon d omega upon d zeta here, d alpha, sorry, not d omega, d alpha upon d zeta, that is change in the alpha with respect to change in the displacement coordinate, that is slope. This is not 0 at zeta equal to 0, or you can say in the small, at small displacement. It is a appropriate word will be at small displacement. So when there is small displacement, this slope is not 0. Okay, but here in this case, second case, change in the polarizability with respect to the displacement coordinate, it is 0. Okay, around zeta equal to 0. You can say at a small displacement. Similarly here, d alpha upon d zeta is again 0 for the small displacement. Okay, it means that when you slightly change that particular displacement coordinate of a polarizability ellipsoid, there is no change in the slope in the second and third case. Okay, that's why these two modes are Raman inactive. Whereas in the first case, slightly changing the displacement coordinate, there is a significant change in the polarizability ellipsoid, or in another word, you can say significant change in the polarizability. Okay, at the small displacement. Okay, so that it can be seen that we can conclude that the symmetric stretching mode of the of that particular CO2 molecule is Raman active. Okay, so this is the case different than the H2O molecule. In H2O molecule, all the three modes are found to be Raman active. Okay, all the three modes are found to be Raman active. Similar discussion can be also applied there in the H2 molecule. Okay, so actually what will happen, slope will be slightly different in the case of the bending and asymmetric stretching mode as compared to CO2 molecule in the H2 molecule. Okay, in H2 molecule, bending mode and asymmetric stretching mode, the slope will be slightly, you can say some value will be there. In CO2 molecule, it's not there. So okay, but actually, what has been observed that the symmetric stretching mode has the intense Drummond line. Okay, symmetric stretching mode will give you the highest intensity of the Raman line. Okay, in both the cases. In H2 molecule, although there there is Raman active mode, bending mode and asymmetric stretching mode, both are Raman active, but its intensity, their intensities are found to be very weak. Okay, so here in the CO2 molecule, both the modes are actually, that is bending and asymmetric modes are actually Raman inactive, so that there is no intensity of that in the spectrum for this. Okay, so that was the discussion about the why CO2 molecule is show Raman active line only for symmetric stretching mode, not for bending and asymmetric stretching mode. Okay, so what from this discussion, what we can say that for the particular mode, maybe the Raman active when there is a change in the slope of the curve between polarizability and displacement coordinate, or at a small, you can, in other word, you can say, so it will be Raman active, the mode will be Raman active when there is the change in the significant change in the polarizability with small displacement of the displacement coordinate. Okay, so in what we can conclude that if the polarizability curve has a large slope at zeta equal to 0, the Raman line will be strong. Okay, if the slope is small or nearly 0, if slope is small, it will be weak. But if it is 0, then it is this mode is not allowed. Let me conclude this in the few lines. These all discussion. If polarizability curve has large slope at displacement nearly 0, at displacement 0, the Raman line will be strong. Okay, if slope is small, Raman line will be weak. Okay, if slope is 0, the mode will be Raman inactive. Raman inactive, not active actually, and no Raman line will observe. Okay, so what you can say that symmetric vibration gives rise to the intense Raman lines. Non-symmetric ones are usually weak, sometimes unobservable. Okay, symmetric stretching mode, it will give you the strong Raman line. So in general, symmetric vibration. Symmetric vibration gives you the intense Raman line. Okay, and asymmetric vibration, it will give you the weak Raman line weak Raman line which may be not observable, which may be unobservable, not observed. Okay, so these diatomic and these molecule H2O and you can say the CO2 kind of molecules, symmetric vibrations gives the intense Raman line. Other vibrations gives the either weak Raman line or the no Raman lines. Okay, so that is the whole crux of this discussion. Okay, crux of this whole discussion. Okay, one more thing I want to discuss here, that the rule of mutual exclusion. Let me just discuss that. Any questions? uh, I hope I am audible, huh?
Yes, sir.
Okay, okay, so let me just
Sir,
yeah.
in three mode, one graph like a cubic graph, and second one and third one graph like a quadratic graph.
Mhm.
But how we can draw that it's a cubic like, it's a quadratic like?
Yeah, actually, the shape of these curves are not important. If you see, the shape is not important. We are interested in the small region actually. Whole discussion, if you see, whole discussion is basically in the small region. It doesn't matter that the shape of that particular curve in the small region. That is around zeta equal to 0. Okay, if zeta equal to around zeta equal to 0, if slope is basically the significant there, if slope is significant there, then you can say that that particular mode is Raman active. Otherwise, you can draw these slopes accordingly, this curve accordingly, but the shape of these curves are not important. Only the discussion around the zeta equal to 0 is important. Okay.
Okay, sir. Thank
Hmm.
you.
So what I want to say that the Raman and infrared activities of CO2 molecule. Let me just discuss. This is important one. Raman and infrared activities of CO2 molecule. So the mode of vibrations and Raman and infrared. So mode of vibrations are like new one. First is symmetric stretching. Okay, and second one is new two is the bending, and these are three fundamental vibration mode. Okay, third one is the asymmetric stretching. So this in the case of CO2, the symmetric stretching is Raman active, bending is inactive, and asymmetric stretching is also inactive. But on the other hand, infrared case, that is the vibration, pure vibration spectrum, the symmetric stretching is inactive. So what we have seen in the case of the vibration spectrum, that there must be change in the dipole moment during the interaction of light with that vibration. Okay, if there is a symmetric stretching, the dipole moment is not going to be changed. Okay, so that you can see that this will be infrared inactive. So in infrared spectrum, it is not, this mode will be not observed. In the bending mode, yes, there will be active vibrations, active infrared, and asymmetric stretching also active. So that what is the rule of mutual exclusion? That if a molecule has center of symmetry, for example, in CO2, this has the center of symmetry. That is the, it has the, you can say, the mirror image of the one atom with the other. Okay, if molecule has, then Raman active vibrations are infrared inactive and vice versa. So this is called rule of mutual exclusion. That is, if molecule is, if a molecule has center of symmetry, then Raman active vibrations Raman active vibrations are infrared inactive and vice versa. And vice versa. Okay. And second is that if there is no center of symmetry, okay, if there is a molecule where there is no center of symmetry, then the some vibrations may be both Raman and infrared infrared active. Okay, this is the case for the molecule having center of symmetry. Okay, for the molecule having no center of symmetry, in that case, what happened? The some vibrations, not all. Okay, some vibrations may be both Raman and IR active, infrared active. Okay, for the molecule having the no center of symmetry, so some vibration, not all actually, they may be both Raman and IR active. I hope I am audible. Harshita, Harshita is saying something. Okay, so this is called the rule of mutual exclusion. Okay, so any questions? Any doubt? Any questions? I hope I am audible.
Yes, sir.
Okay, so if there is no question, then I can go further. So I want to now discuss the vibrational Raman spectrum. Okay, so this is going to be the last article in your syllabus. Okay, so this actually our syllabus is almost complete. So I was just looking at the syllabus. So in your syllabus, the Raman transition is there, but it is only for the CO2 molecule and H2O molecule and the three fundamental vibration only. Okay, so this is going to be last one. So let me just discuss this vibrational Raman spectra. Okay, so this is very simple in the vibrational Raman spectra. So you can just write the energy of the vibrational spectra like this. So we have E is equal to omega E. That was the V plus 1 by 2 minus W E X E. It was like V nu plus 1 by 2 square centimeter inverse. Okay, so here this WE is nothing but what was it? WE. This was the equilibrium vibrational frequency. This is the equilibrium vibrational frequency. And what was the XE? XE was the enharmonicity constant. Enharmonicity constant. Okay, we had this delta, this nu was equal to, these are section rules. These were 0, plus minus 1, plus minus 2, and so on. Okay, so let us take the example of the Raman active modes. Let us find out the energies for the Raman active modes. So Raman active modes, first one can be like nu equal to 0 to nu equal to 1. Okay, so this is transition from 0 to 1, nu 0, nu 1. So you can just put the, this is question number 1, you can just put the value of 0 and value of 1 in the that equation number 1 and try to find out the difference. Okay, so that this will give you the delta E, that will be fundamental transition. Delta E fundamental transition, which we have already discussed in the vibration spectrum. Delta E fundamental. So when you just put the value of 0 and 1 in the equation number 1, try to find out difference, you will see that it will be omega E 1 minus 2xe centimeter inverse. Okay, another mode can be nu equal to 0 to nu equal to 2. So these are basically the vibrational quantum number. Okay, so we had discussed in these vibrational quantum number when we were discussing the vibrational spectrum. So this is the overtone. This transition is called the overtone. There was the first overtone, second overtone, third overtone, and so on. Okay, we had discussed that. So this is delta E overtone. This is called overtone transition. And this is given when you put the value of 0 and 2, find out the difference in equation number 1, you will see that it will be 2 omega E 1 minus 3xe centimeter inverse. Okay, another mode of another Raman active mode can be transition from nu equal to 1 to nu equal to 2. So that was not discussed previously in the vibrational spectrum. This is actually called the hot band, delta E hot. So when you put 1 and 2 in the equation number 1, okay, V equal to 1 and 2, find out difference, you will see that it will be omega E 1 minus 4xe centimeter inverse. So why it is hot band? It is hot band because there is a transition between the excited states. So in this nu 1 and nu 2, both are excited states. So that's why it is called the hot band or hot transition actually. Whereas the other two transitions are from the ground state to the excited states. Okay. So first ground state to the second. So we have the two different levels. So inside that different levels, we have different value of nu. Okay, so transition from 0 to 1, it will be like fundamental transition. 0 to 2 is the overtone transitions, and 1 to 2 are called the hot transition. Okay, although all these three, you can also find out other transitions. Okay, although all the transitions are Raman active, but intensity of these other transitions are going to be very, very weak. So Raman line will be going to be very, very weak, and sometime it will be unobserved. It is not observable in the spectrum. So that's why let us confine ourselves in the fundamental transition only. Okay, although these transitions are available, these are available in the spectrum, but these are going to be very, very weak, sometimes not observed overtones and hot transitions. Okay, so let us restrict ourselves in the this first fundamental transition. Okay, so that the if you find out the the fundamental from the exciting line. So you must have, so when we were discussing Raman spectrum in the rotational Raman spectrum, you have seen that there is some exciting line, okay, around which there will be some lines, some other the lines which are in the case here it will be fundamental transitions. So around this exciting line, the fundamental transition can be written like this, that we have new fundamental it will be equal to new new exciton new exciting line plus minus we have delta E fundamental. Okay, so we have restricted ourselves in the fundamental transitions only. So this will be exciting line plus minus delta E fundamental centimeter inverse, where we have plus minus sign. Okay, this minus sign represents the Stokes lines. Okay, and the positive sign it will represent the anti-Stokes lines. Negative sign in this expression, this will represent the anti-Stokes lines, the Stokes line, sorry, Stokes lines, where the energy is molecule gain energy, where the molecule gain energy from the where the molecule gained energy from the radiation. Okay, then positive sign, it is the anti-Stokes line, where molecule lose energy to the radiations. Okay, so this was the mathematical expression for the vibration Raman spectra, where we will have the fundamental. We are discussing only fundamental transition, which are the which have the intensity that can be observed in the spectrum. Okay, other transition we are not discussing here, because other type of transitions are also available. Overtones and whole transition will be there, but their intensity is going to be very weak, and it is actually very difficult to resolve in this spectrum. Okay, so we are only discussing the fundamental transition, and around this exciting line, there will be a Stokes and anti-Stokes lines. Okay, and if you see the spectrum, typical spectrum of the typical Raman spectrum from the spectrometer, it will looks like that. So we have typical Raman spectrum from Raman spectrometer. So actual spectrum, how it will looks like from the spectrometer. So if you draw like this, so it will be like this. This is for a particular molecule, CHCl3. Okay, this is for CHCl3. This was experimentally observed spectrum, and it is already given in your book. Okay, so we have the different. So we have exciting line here. This is the V exciting line is here. Okay, so spectrum was like this. So typical spectrum is like this, so Raman spectrum. This is the exciting line, and here it will be like this. So it was in centimeter inverse scale, and it is about 3200 centimeter here, and here it is around 2000 centimeter inverse, 1500 here, and these lines are around, these are the 100, it's 1000, then we have 600, okay, and so on. We have here 300 like this. This is a typical Raman spectrum which has been observed experimentally for the symmetry top molecule CHCl3. Okay, these are the Raman active lines. You can see these are the Raman lines which can be observed in the spectrometer for a particular molecule. Okay, so that was the Raman vibrational spectrum. And with this, I think this syllabus is complete. I was just looking at the syllabus. So in your syllabus, only CO2 molecule, H2O molecule, and fundamental transitions only it is given there. So with this my part is complete. Okay, that was a 1 credit unit. Okay, for Raman spectrometer and Raman vibration spectrum, rotational spectrum, and Raman spectrum. These were the all main topics of this particular unit. So any questions, any doubt, any query? Any doubt?
हेलो सर सर
Yes,
सर
yes, please.
सर आपने असाइनमेंट दिया था सर उसे सबमिट कहाँ करना है सर
Assignment दिया था?
यस सर आपने वाइब्रेशन एंड हार्मोनिक मोशन के लिए सर वो आप वाइब्रेशन के लिए आपने दिया था सर तो वो हो गया
असाइनमेंट दिया था? मुझे याद नहीं है.
यस सर दिया था आपने
ओके, वाइब्रेशन असाइनमेंट कब दिया था मैंने? मुझे याद नहीं है. किसी और को है दिया? सबको दिया है?
यस सर
ओके ओके,
यस सर ये चल दिया है
दिया है ना. सो व्हाट वी कैन डू, आई विल, ओके, सो ऐसा करो, तुम मुझे ऑफलाइन सबमिट कर दो. सबमिट ऑफलाइन. ओके ओके, ऑफलाइन जो भी तुमने किया है रिटर्न में, सबमिट ऑफलाइन इन माय ऑफिस. ओके, एक सबको इकट्ठा करके ले आओ एक बार ना.
ओके सर
ठीक है. एंड मे बी नेक्स्ट वीक आई विल टेक वन एग्जाम, दैट इज द सरप्राइज टेस्ट, है ना. 10 नंबर का मैं एक बार ले लूंगा नेक्स्ट वीक में. आई विल टेल यू मे बी ऑन नेक्स्ट फ्राइडे. ठीक है.
ओके सर थैंक यू
सो लेट मी टेक द अटेंडेंस. या यस प्लीज.
सर कौन सा असाइनमेंट दिया था सर
इनसे पूछ लो, वही विनोद एंड अदर्स, इनसे पूछ लेना कौन सा था ना. मुझे खुद याद नहीं है अभी कौन सा दिया था मुझे. ओके, सो अटेंडेंस प्लीज. 13. ओके, आलोक कुमार महंता.
यस सर
आलोक कुमार, आप लेट क्यों आते हो? हमेशा मेरी क्लास में लेट आते हो 15-20 मिनट. जितनी मैंने अभी 6 महीने में क्लास ली है, लास्ट सेमेस्टर भी, सेमेस्टर भी, हमेशा आप लेट आते हो क्लास में. वाई? Are you hearing me?
यस सर
You always come late in my class. Not today, but every class I have observed. और लेट भी 5 मिनट 10 मिनट नहीं होता, हमेशा 15-20 मिनट लेट आते हो. अंजना विंसेंट.
प्रेजेंट सर.
असगर अली. अतुल कृष्णा. ब्रह्मनंद बेहरा.